For some reason, I don't know why it wasn't drawing a dot product. The dot product, here's what it looks like. You got your V, and it's like this dot that you can see, dot product. So I don't know why it was not working so well, but there you go. Those little boxes are supposed to be dot products. Okay. Okay. So let's see. You got the little formula up at the top here. Your x1 and x2. So this is going to be my x1, y1. And then here's my x2, y2. So to find my dot product, I'm going to do the x1, x2. So like 3 times 1. Plus my y1, y2. So like 4 times -2. All right. So it ends up as a single number here. All right, so I'm going to get a -5. My dot product is a single number. Okay. All right, so you guys take a sec, find your dot product on example 2. We'll start calling and see what we get. So, and Ian, it's Murphy as well, right? Ian Murphy, same diff. Remember? Okay, just making sure. All right. Okay, so constants, let's see. Let's see, Shara, what'd you get for your answer on number 2? What was your dot product here? Yeah, it's supposed to be V dot W for some reason.
Sorry, I'm still working on it.
Okay, let me know what you got when you're done. So I'm gonna wait for Shira while we're waiting. I'm gonna look at example 3, where again it's supposed to be a dot product. Was your dot product is a single number? So on my next one here, my dot product x1 y1. Here's my x2 y2. All right. I'm gonna multiply my x's together. So like a 2 times 1. Multiply my y's together, so -1 times 4. Okay, so the stuff in the middle here, that dot product is going to be, let's see, a 2 minus 4, so -2. Now, like I said, that's just the dot product there. What I haven't messed with yet is multiplying by a vector. So I'm doing like a constant, -2, times my v vector. Here's the v vector, the 2, -1. I've got that dot product, that constant in front of them. So if I distribute that, I'm going to end up with a -4 and +2. All right, so that kind of combines my dot product with a vector. Any questions on that one? Dot product is a constant. That's the part that I'm trying to like drill into your head. Your dot product is a single number. It's a constant. All right, and then Shara, what'd you get for example 2?
I got -2.
-2. All right, is that what we all got? Yeah, that's what I got as well. Nice. -2. Okay, so that was my v dot w. All right, so on part B here, there's a little change. They want, yeah, and this is supposed to be a dot product, v dot 2w. Let's figure out what the 2w is first. Okay, so let's see, my 2w is, here's my w. I'm going to multiply all those by a 2. So I get like a 2/8 for my 2w. All right, and they want my v dot the 2w. So if I use these guys, here's my v, here's my 2w vector. let's do a dot product with these guys. Okay, so that's where I do my x's multiplied together plus the y's multiplied together. So I'm gonna do a 2 times 2, so 4, plus my y's, so like a -1 times 8 is a -8. All right, so this one, overall dot product, so an overall constant of -4. Okay. Do I have any questions yet? You guys at home, we doing all right?
Yep.
Yeah, doing good. All right, so nice. Let's go to C then. I think this one should look somewhat familiar, right? Does that double line thing look like something we've done before? Yeah? What's it called? Magnitude. All right. So that one kind of looks like your distance formula or Pythagorean theorem. It kind of looks like familiar work that we've done before. So for that, I'm going to, oh, hey. Do my little magnitude formula. So this was for just the W, right? Just the one that had blue. So I'm just gonna do the 1 squared and the 4 squared. So let's see, a 1 plus 16, so a square root of 17. There we go. All right. So I think the new stuff so far has been the dot product. Magnitude we've done before, multiplying by constants we've done before. I think the main thing in this section was the dot product, and we're gonna then step it up right here. Let's find the smallest angle between two vectors. The reason I say the smallest angle is because if I have like, here's one vector, here's another vector, there's kind of two angles you can consider really. There's this, here's my smallest angle, and then there's this other really large angle as well. So we're just considering the smallest angle. Okay, so find the smallest positive angle between each pair of vectors. Let's see, according to this cosine of alpha, I'm going off of this right here. Cosine of alpha equals, oh, my alpha sucks, there we go. See if I can draw a pretty alpha. Huh? There we go. All right, this is supposed to be, again, a dot product. I don't know why it's not typing well, but there we go. Our dot product is in the numerator over the magnitudes in the denominator. So that's why we were just practicing dot products and magnitudes. Okay, so my dot product in the numerator, my x's multiplied together, so -3 times 4 is a -12, plus the y's multiplied together, so my 2 times 5 is 10. All right, over, that's my dot product, over the magnitudes. I gotta do the magnitude, that was a big old square root, right? Let's do that of our first vector. So like the -3 squared plus the 2 squared. So there's my first magnitude. I got to multiply that by my second magnitude. Let's see, I'm going to extend this here. That's magnitude of my second vector, so 4 squared plus 5 squared under my square root. All right, all right. Honestly, this is really messy, but doesn't cosine usually equal these messy numbers? And then we do the inverse cosine to get our alpha. So whatever calculator you've got, let's bust that out. Make sure we are in degree mode, first of all. So I'm going to see what kind of messy decimal this is. Looks like I've got -12 plus 10, so like -2. Oops. Divided by, and in the denominator, I've got two different square roots going on here. So I put a parentheses, so I'm going to do the 2 square roots multiplied together. So it looks like I've got the square root of 9 plus 4. You guys know where I'm getting this 9 plus 4 from? All right, that. Okay, so my 9 plus 4 is a 13. Honestly, you could type this messiness in if you want. I just was looking at a 9 plus 4, so 13, and this one 16 plus 25, right? Where am I at here? Okay, so my 16 plus 25, what am I at, 41? So times my square root of 41, okay. Put that in parentheses, there we go. Messy decimal. I like that it's between -1 and 1. Isn't cosine supposed to be between -1 and 1? All right, that's a good sign. -0.08, blah, blah, blah. I'm not going to mess with it in my calculator. I'm gonna keep that whole thing in my calculator. And now I'm gonna do the cosine inverse of that incredibly messy decimal. Maybe I'm gonna put like a little ... like I've kept the whole thing. It's gonna give me my alpha. So this is my smallest angle. So cosine inverse of that whole shebang there. All right, so it looks like I got, on your homework, do they have you round to the nearest 10th, 100th? What do they usually do? 100th, okay. So I'm going to the nearest 100th, that would be like 94.97. And we're talking degrees here. This was an angle in degrees. All right. Any questions on part A here? Like you guys can do this on your own. Okay, if you guys can do this on your own, let's have you guys do part B and we'll see if we got it. Yeah, you guys online, just type it up here. Let me know what you got. Okay, so Eric, good question. How do I know if that was the smallest angle? First of all, it's a little over 90. And visually, you can see if it's a little over 90, this would be smaller than the rest of the 360. 360 is a full circle, right? Also, your your calculator has restrictions on what it'll give you. And yes, it will, I think 180 is the highest it can go. So you'll know that you have the smallest alpha of your calculator as well. So a couple reasons.
B is 0.
All right, Marcus got a 0, you got a 0. Are we all getting a 0?
I got 90 degrees.
Yeah, if you complete the first step, it's automatically 0. And since the top of the fraction is 0, then the rest is going to be 0.
Talking like, okay, are we talking like 0 degrees? Because we're finding an angle, right?
Yeah, like the cosine is 0. So that makes
Oh, so you got this cosine of alpha to equal 0. But we need to know the alpha. We need to know the angle.
Yeah.
So let's get our angle.
Oh, it's 90.
Oh, there we go. Okay. So let's check this out. Cosine of alpha. It looks like you guys had cosine of alpha equaling 0. Let me kind of make sure we know how we got 0. It looks like I did my A dot B, which, okay, that gives me -5 times 9, so like a -45 plus, okay, I multiply my y's, I get a +9 times +5, so a +45, which I'm assuming that's where you guys got your 0, right? All right, and then honestly, these are messy magnitudes down here. I think they were like, was it in the hundreds, I think? They're both the same though. They're both gonna be like -5 squared plus 9 squared. -5 squared is what, 25? Plus 9 squared, 81. My other one also. What? Oh, 106, yeah. Yep, and my second magnitude is actually still gonna be a 9 squared, so 81. And a 5 squared, so 25. So this is also the same square root, right? All right, so honestly, I'm not even too worried about that though, because 0 divided by whatever, as long as it's not 0 divided by 0, which this isn't. So 0 divided by whatever is still going to be 0. So I'm going to have cosine of alpha equals 0. And it looks like this is what most of us were getting, but we were kind of thinking this was our answer. Yeah, we have to solve for the alpha to get our answer. That's why we had to do our cosine inverse of 0. We're talking in degrees. We get 90 degrees, which this I think you guys had memorized on the unit circle, right? 90 degrees on the unit circle gives you a x value of 0, so your cosine is 0. So I really probably didn't even have to put that in my calculator. So Nicole, for now, maybe go ahead on to like Desmos or something, and we'll see if we can figure that out. We can't do that on like the test or whatever, but for now, let's use that just for a little bit here. All right. So my angle that we were going for, 90 degrees was my angle. Okay. Any questions? Speak now if you ever hold your peace. Girls? All right. Okay. Let's go on to these ones then. Orthogonal. Orthogonal vectors, two vectors that are perpendicular to each other. So yeah, orthogonal in my head kind of triggers like 90 degrees when I think of orthogonal. So this symbol is used a lot of times. This would be like V is perpendicular to W. So the angle between them is 90 degrees, and that's when your V dot W equals 0, which, ta-da, this is what we had up here. Your dot product that we had in the numerator was a 0, and that led to having orthogonal vectors. They had 90 degrees between them. Okay, so this one says, what does K have to be for the vectors to be orthogonal? Like they've got to have their dot product of 0, right? Yeah.
-1.5.
How'd you get that?
Because we need 2 times K to equal -3 because
So you're doing your dot product kind of thing being 0?
yeah.
Okay. Which your dot product was the 2 times K, the like the x's multiplied together, plus the 3 times 1. That's supposed to be a 0?
Yeah.
Right?
So,
Okay.
yeah, 3 times 1 is 3.
Yep.
And so it, we need 2K to equal -3.
Nice. Okay.
2 times -1.5 is -3.
That is true. I think another way I was looking at it is I divide by 2, but yeah, I get to -1.5, -3/2. I don't know about you guys, my newbies here. I'm pretty lenient, or I'm pretty hesitant with decimals. I usually go toward fractions, especially when my decimals have to be rounded. If I don't have to round, I'll go with fractions. But yeah, in this case, I wouldn't have to round. So if you put like a -1.5, I would be okay with either one of those. Yep. Looking good. So we found the K. That's all I wanted us to do. What does the K have to be? I don't care if it's the -3/2 or the -1.5, either way. But yeah, I think honestly on this one, you had to know the vocab. Otherwise, it'd be a bit confusing. If you knew that the vectors are supposed to be orthogonal, it's like, okay, all right, my dot product is 0. That's kind of the translation here. That means the dot product is 0. Okay. All right. Any questions so far? Girls, we're doing all right? Okay, we're gonna use some more dot products. It's supposed to be a little dot product right here. U dot V. Okay, so the projection of U onto V. So this is how they're writing. I think this is new actually, how they're doing in this book. They're writing this little subscript of V. That's what we're going on to. We're going on to V. And then the stuff that's in the parentheses here, that's what you're taking the projection of. And so here's the little formula for it. Get rid of that. Here's my little formula for it. So example 6, they gave you a U, they gave you a V vector. They want you to find this P. It's the projection of U onto V. So I'm pretty much going to use the 2 vectors they gave me for the formula. It requires the dot product. It requires some magnitude. So kind of the same stuff we've been working on. But keep in mind, this vector on the outside is going to be multiplied by the stuff in the parentheses. All that stuff in the parentheses is going to end up straight up numbers. My dot product is just a number. My magnitude is just a number. So this is going to end up just a single number multiplied by my vector. Okay. So let's see what kind of number we get. I'm going to do my dot product. Did anybody actually do the dot product already? U dot V? You guys got it? In the teens, what was it? You, 15, okay, I couldn't hear if it was 15 or 16. You guys got a 15? And I think I did this earlier, 15, that's what I got as well. It was like -1 plus 16. So you get a 15? Okay. So yeah, sorry, I'm just gonna slow this down for a sec here. My 1 times -1 is a -1 plus, and then my 8 times 2 is a 16. So that's where we were getting our 15. That's our dot product in the numerator. All right, denominator, we've got some vectors, the magnitude of our vectors and squared, which, okay, isn't the magnitude formula like a big old square root? And then you're like squaring this square root, right? So that might make things nice and pretty. You've got your magnitude of vector v. Okay, here's our vector v, meaning the square root of the -1 squared plus 2 squared. And you want your magnitude squared. This whole guy is squared. So like my square root is squared. That's kind of nice. That means they kind of cancel out, right? Square root, squared exponents, those are inverses. Bam, gone. Which means all I have left is -1 squared plus 2 squared. So like 1 plus 4 is a 5. All right. And again, I'm looking for the stuff in the parentheses. I'm getting that constant term that I'm going to multiply by my vector, which it looks like 15 divided by 5 is a 3. So this constant right here is going to be a 3. I want 3 multiplied by my, it says v, right? The vector v. Okay, so if this is a v, here's my v. I'm going to multiply it by the -1, 2. Which, let's see, that means I distribute by my 3. So I'm going to get a -3, 6. And we're done. It is a vector though. This one is not a single number. This one is another vector. Okay. You guys at home, how are we doing? I haven't really heard very much.
So good.
So good. I like it. I like it. Good. You guys okay? All right. So I'm going to go on to this one, which this is kind of how the book does it. So like if you guys, do you guys ever look stuff up in the book to kind of see how to do certain problems? Or do you guys click on the like the videos or stuff from the homework? So this is probably how they'll explain it. Honestly, we think there's a little better way to do it, but this is how they'll do it. They'll say, okay, so Pooh has a 200-pound cart of honey on a ramp inclined at 30 degrees. What force is required to keep the cart from rolling down the ramp? So the first thing they do is they find the force, which here's my J, because they use the word down, going down. My I's are like my X's, horizontal. The J's are like my Y's, vertical. And so I would have like a -200 J, like going down by 200. And then you've got your V, this V vector here. They're using their 30 degrees. There's your ramp inclined at 30 degrees. Honestly, in my head, when I do this, I don't know about you guys, but I kind of picture a ramp like this. And I kind of have in my head like a triangle. So that's how I would do it. I would do it with like 30 degrees right here. All right, and then you've got, let's see. This is kind of actually what we did last time. You kind of draw a triangle right here. I'm gonna make this into a right triangle. All right. So the reason I drew it like that is because my force of gravity, doesn't gravity pull you like straight down? So like this force of gravity, that -200 J, that's like the -200 that's pulling like straight down here. Does that make any sense? There's my gravity pulling straight down. And actually these triangles are congruent. And by that, I mean, this angle right here is 30 degrees also. All right. And it says, what force is required to keep the cart from rolling down the ramp. So let's see. Here's my ramp. Isn't rolling down the ramp, that would be like, oops, I erased it. That would be like this side right here. That'd be like rolling down the ramp. So personally, I'm going to consider this right triangle. And then off of right triangles, you can use whatever trig function, right? This one with a 30, I think the x is opposite of my 30. The 200, is that the adjacent or the hypotenuse? Hypotenuse is across from the 90 degrees on that triangle. So that's the hypotenuse. Let's see, opposite and hypotenuse, that would be sine. So I personally would go like this. Sine of 30 degrees equals the opposite over the hypotenuse. So like the x over the negative 200. And at this point, this is an equation we learned how to solve. Multiply the negative 200 over, you can put it in your calculator and get your x. So the way they do it obviously is a little different. It's more scientific. I did it more mathematically. There's a little more scientific, but we should end up with the same answer. So I'll show you what I mean. I would get, if I put this in my calculator here, I'm going to multiply that negative 200 over times my sine of 30 degrees. All right, so I got a negative 100, right? Oh, look at this. They had a negative 100 as well. Crazy. So they went through like a longer process, I suppose, but they said what force is required to keep the cart. This force, honestly, this is what I had to learn more about. That force is basically giving me, it's asking me for the magnitude. So it's basically asking me for the magnitude, which in this case is a negative 100. So either way, I end up with a negative 100 for my magnitude. I personally tend to do it more mathematically. I do it with the triangle. But either way, I get the same answer. So honestly, I'm not going to focus on this stuff too much. The reason I pointed it out is because when you guys watch videos or whatever you guys do on that website, they're probably going to explain it this way. Okay. All right, let's see if we can do this again though. So you guys look at number 8. Very similar to number 7, different numbers, but let's see if you guys can deal with, I don't care which method you use it in, I'm going to do the triangle one. Let's see if you guys can find the force though, find basically the magnitude. With the given information. So I'm going to give you guys a second, then I'll start asking what we got. How we doing, guys? You good there? You guys at home, how we doing?
All right.
All right, we're getting there. Still working on it, okay? All right, Tristy, where'd you get stuck so I can know what to focus on? Is it like the drawing the triangle? Is it labeling stuff? Maybe setting up the trig function? What kind of stuff did we get stuck on?
So what's the difference between a problem where we would have to say, find, this was required to hold the card, what is the difference between the force required to pull the cart and the force required to keep the cart from rolling down the ramp? It seems that we would do the same thing each time.
Well, so I guess the difference between pulling it down the ramp and keeping it to stay the same is you've got to be exactly the same. You got to be totally equal if you're going to keep it like still, right? If you are keeping the cart from rolling down the ramp, it doesn't say pulling it. Like you're not having to move in a certain direction. They just want you to be equal to what's going in the opposite direction, if that makes any sense.
Okay, but how would we change it?
So what was that?
How would we change the equation if we were trying to pull the cart?
So in my head, it would have to be like an inequality as opposed to an equal sign. Like you would want to be greater than that to pull it, as opposed to equal to it to keep it there. Does that make any sense?
So,
Sort of?
because yesterday we had problems where, it gave us the force,
Uh-huh.
but we had to find, like the weight of the trailer or something.
Okay. Which a
Um,
weight is a constant, right?
Yeah. But it said pulling, not keeping it still, so we have.
It's probably asking for the barrier, like it has to be across what amount, has to be greater than what amount.
So why didn't we do it inequality yet?
Let's look at it and we'll see. I want to see the way they worded it again. Wait, hang on, this one says. Okay, so the triangle, yeah, so let's look at the triangle on this one. Where did there we go. All right, so very similar. You got this ramp, right? Kind of treating it like a right triangle, but you guys know going straight down, okay? This was my 150-pound cart. That's like how much it weighs goes straight down. So here's my 150. Is that where you guys put your 150? Yeah. And I guess in my head, how the weight of something, that your pounds, your weight gets pulled straight down when you hop on a scale or whatever, going straight down. Then this other one, we're gonna go at 90 degrees here. All right. With a 15-degree incline. So here's my incline. Honestly, this is what they're talking about, but I'm just drawing a congruent triangle. So I'm going to put that 15 degrees down here. That's congruent to the other triangle. And they want to know what force is required to keep the cart rolling down the ramp. So we're talking about this X force to keep it from going down that ramp. All right, so which trig function do you guys go with? Sine, cosine, tangent, any of the inverse, like what'd you guys go with? Sine, again, same sign. You've got, according to your 15 degrees right here, we've got the opposite, and then the 150 is my hypotenuse across from the 90. Yeah.
Would it be negative 150? On the side of the force?
That's what we're doing.
Like
Pound. Oh, so you're saying you're, thanks, yeah, you're negative. Let's adjust that. So it is pulling down, you're right, because magnitude and direction matter. So the magnitude is 150, but yeah, your direction is going down by, there we go, yeah.
Why does the X go? where you put it?
So the X goes where I put it because this is, so your force, like the magnitude to keep the cart from rolling down the ramp. Here's my ramp. This is my ramp, right? So if you're rolling down the ramp, it's like going down that slanted ramp there. So I'm going with the force to go down that ramp. That's where I put my X there. Yeah, no. Do you have a question? So why would I put that X somewhere else? Like, why would I put it like over here or something? Why would I put it like right here? Is there any vocab in there that tells you to put it in any other spot? I think in my head, I'm visualizing a cart rolling down a ramp is right here in my head. That's kind of my visualization. That's why I put the X right there.
But, the side the side that the ramp corresponds to is the hypotenuse, which is where we put the 150.
But I'm looking at this smaller triangle, so it's not the hypotenuse of that smaller triangle. It is opposite of my 15 degrees on that smaller triangle. So I'm making the X go this distance right here. It's not the whole entire ramp. It's on the ramp, but it's that distance that has to do with the small triangle or the one that I rotated, the one that's facing down. I'm looking at that triangle.
But you keep highlighting the bigger hypotenuse side when you were referring to why you put the X.
So I keep going like this because I'm talking about a ramp. I'm visualizing that as my ramp that I'm going up or whatever. So that's why I was drawing a line right there. The X itself is for that like vertical triangle that we're looking at. The X itself is going from here to here.
I understand that. I don't understand why. Like, why wouldn't you put it on the side adjacent to 15 or on the top?
So adjacent to the 15 or so the hypotenuse I already know is the 150. And this side right here, we're talking about force required to keep the cart from rolling down the ramp. That would be, okay, so say the cart's sitting right here. If you pull right here, is that going to keep it from going down the ramp? I don't think so. I would want to pull my magnitude on the ramp, actually on the ramp. That's why I'm looking at this guy. There we go. So I've got my sine again, but I've got 15 degrees this time instead, equals my opposite over hypotenuse. I'm gonna multiply by 150 to the other side. We're gonna get another negative here. So let's go to 2 decimals again. I'm gonna do sine of 15 degrees times my negative 150. What do I get?
Negative 38.82.
Negative 38.82. All right, so there's that guy. Which, okay, let's take a sec here. I think this is pretty much the same thing, so I'm gonna, are we good with 7 and 8? Are we okay if I skip 9? We good? It's still more Eeyore, you got some more Pooh Bear triangles. Okay, I'm gonna look at, I know it's a different problem.
Hold on, really quick. I'm a bit confused on what you do afterwards.
After what?
I mean, after we find X, it's just, I mean, I'm looking at step 3. It's just I can't follow on much what it does.
So that's, after I find X, like I'm done. That is my force that is keeping the cart from rolling down the ramp. That's my X there. I'm actually done with that. That's what I was done with up here as well.
Oh, I see. Right. Thank you.
Yeah, and I circled it in green right here because the stuff that they did on their work, their answer ends up being the magnitude ends up being the negative 100 either way. Because if you're looking
Right.
for the force, just the magnitude, either way, I get a negative 100 on that original one, or I get a negative 38.82 on this one.
Right, if you don't have any questions for yesterday's homework, can we go?
So hang on just a second here. Let's see. Oh, yeah, it's Eeyore. Let's talking about Eeyore on the next one. So what I want to talk about from yesterday, we went and we went and talked to our science teacher here. Got a better explanation. Let's see.
Is example line not, I mean, is example line the same type of problem?
Yeah, it's the same type of problem. Still a triangle stuff. It's still the same type of problem on that one. So this one was from yesterday. And as far as the explanation on this one goes, when you're pulling this, boat up the ramp or whatever, remember this yesterday? And people wanted a further explanation as far as like, why would it be this high of a number, bigger than my 600 pounds, to pull the boat up the trailer, boat and trailer up the ramp? And so I was talking to our science teacher, and they were saying, okay, well, when you go in a different direction, you've got a totally different vector. You've got totally different things playing in the game here. Like, so the yellow one, the gravity going straight down, that boat would have to like go through this, cement or whatever. It would have to like really have some effort to go straight down, versus the different direction going up. I guess it's not the exact opposite direction, but it's a different direction. It's a different vector going up. And so its magnitude, some people were like, how is this so much less? How is that 600 that we found, that they gave us? Why is it so much less going that way? And so his good explanation was that this has totally different, I guess, effects to the ball game here. You've got like a wheel, right? I don't see like some barrier. I don't see like a wall it has to go through or anything like that. So this different vector going in a different direction, it has different magnitude required. And in this context, some of the stuff where like the wheels, this stuff going through that's like cement or whatever makes it way higher. So that was a much higher magnitude to go straight down. So I know that was one of the questions we were having yesterday. So I hope that helps clarify a little bit why that huge number was so huge. All right. And then as for your homework yesterday, these guys, so I made a video of it. So I'll post that. You guys can also take a look at these from your homework from yesterday. This top one right here, they drew a picture for you, which is kind of nice. This one, they didn't draw a picture for me, but I kind of did like I was talking about today. I kind of did it into some trig, Do you guys have questions on these guys from your homework? Yeah, which ones do you need to look at? Because I'll be quicker on these ones. I already can post a video on these ones, but
The tugboat one.
the tugboat one?
And that's 17 on my homework, and then 15.
Okay, so Trissy, this one's 17 for you as well? Okay, so it looks like a bunch of us, I thought a bunch of us had this question. That's why I kind of prepped for that. Okay, so this one, the nice thing is, notice that they have 18 degrees and 18 degrees. They're both going like at the same angle from that. I'm gonna treat this like my x-axis. They're going like, that's what the black stuff is here. I'm treating this like a graph. I've got like 18 degrees above and 18 degrees below, which, okay, instead of calling this like a negative 18 degrees, I think if I do 360 minus 18, I get this 342 degrees, because that's what we're used to doing on a positive angle, right? We go this direction, I would go 342 degrees to land in that vector. All right, so that means my A and my B, I made their own little vector. So here's my A vector. I don't know the magnitude of it, but I do know that it's at an angle of 18 degrees. This B vector down here, again, I don't know the magnitude of it, but I do know that my angle there was 342 degrees. So that's why I set up these two vectors. And then when I add them together, when I combine them, It's like, let me erase, that's like the purple stuff here. It's going down my like x-axis, which the way they said it was along the axis of the barge, find the tension in the tow lines if they each make 18 degree angles with the axis of the barge. Okay, so yeah, they're towing a loaded barge and the magnitude is 2,400 pounds directed along the axis of the barge. So it's going along this axis right here. So that's kind of what tells me we're going horizontally there. I had a positive 18 degrees and negative 18 degrees. I got this. Is everybody okay with the two vectors here, my A and my B vector? I don't know the magnitude of those vectors, but I do know the angles. All right, well, because I know it's gonna go down the x-axis, I know that my y's, like on this purple stuff right here, my y's are 0. Like all this sine stuff, that's why I kind of crossed out the signs here. My signs here, they're 0. And then I guess it adds up to 0. I'm gonna have this guy, if you can do it in your calculator if you want, but sine of 18 degrees plus sine of 342 degrees, you can put that in your calculator, it's gonna be 0. They're gonna add up to 0. And then cosines though, cosines are my x's. Let's see, that means I gotta keep those x's. I've got cosine of 18 degrees. I've got cosine of 342 degrees. They've got the I on there. It's true, the I is just telling me which direction though. The I means I'm going like horizontally. I factored out the magnitude. I still don't know what that is. So I factored it out, got this stuff left over, and I put all this messiness in my calculator, which was like this 1.9 blah, blah, blah. It's like this long decimal, right? But I divided it over. I'm trying to get the magnitude. The whole goal here is to solve for the magnitude. So once I figured out what my cosine of 18 degrees plus cosine of 342 degrees, whatever, I figured out what that was, I divided it over to the side of my 2400, and I got my magnitude, which, should look and see what that was. Oh, actually, you can see up here. It was supposed to be like 1,261.8. And notice it was the same on both of them. My tugboat A and my tugboat B have the same magnitude, which kind of makes sense. They're both at the 18 degrees. They both are the same, like tugboats, that everything's the same on them. So they had the same magnitude for those guys. Okay, so is this helpful on this problem setup? Yeah.
I also found with this one, if you take your first, like the 2,400 pounds,
Uh-huh.
and then if you divide it by the cosine,
Okay, yeah.
and then you divide it again by 2.
By 2, totally.
It'll give you the answer.
Yeah, that totally works. Totally works. All right, you go. So Trissy, are you okay with this one? I think you were talking about 17 here. This was 17, wasn't it? Okay, okay. All right. This one I think is similar to what we did. The other one you guys were talking about. Yeah, no problem. I don't have that open. Do you have the other one that you were talking about open?
Yeah.
What does it say?
Is it okay if I log off?
Yep, you can.
A gun with a muzzle velocity of 1,240 feet per second is fired at an angle of 7 degrees above the horizontal. Find the vertical and horizontal components of the velocity.
The vertical and horizontal components of the velocity. So sorry, I heard something about 7 degrees from horizontal.
Above the horizontal.
Above the horizontal. So like this, 7 degrees going up from my horizontal. Okay, and sorry, what was the rest of it?
A gun with a muzzle velocity of 1,240 feet per second is fired at the 7-degree angle.
Okay, so this is my magnitude going right here. It's fired at that angle going increasing up, right? All right, and I'm sorry, I'm just with the mask, it's hard to hear what you're saying.
1240.
1240, like that?
Yes.
Okay. All right, and what do they have you finding?
The vertical and horizontal components of the velocity.
The vertical and horizontal components. So kind of these guys, right? Which in that case, if I kind of do the trig stuff that I'm talking about, I'm going to, maybe I'll just put my X right here, or maybe my V, my vertical, whatever. But now that's like opposite and hypotenuse right here. So I'll do some opposite over hypotenuse, I'll do some sine for that. And once I'm done with that, I'll get my horizontal stuff. I'll use the horizontal and the hypotenuse, like my adjacent and hypotenuse. I'll do some cosine on that guy. I should be able to get my vertical and horizontal based off the triangle. Does that help at all? All right, those at home, just make sure you guys do your 6.4 homework tonight, okay? 6.4 on WebAssign. Other than that, you are good to go. Those of us in the classroom, let's go ahead and wipe down our desks.
All right, thank you so much. Have a good day.
You too, see you guys. Yeah, what's up?
I looked up a question to see if this would help explain anything further.
Oh, yeah?
An average